Right, so we all know that we store fat in our body and that that's an energy source, but beta oxidation is how we actually use that stored fat to produce the energy. Now, in the corresponding blog post, which is linked in the bottom, we talk about how stored fat, because fat is stored as triglycerides or triacylglycerols, is split to release glycerol and 3 fatty acids. I'm not going to be going into that into this video because this is a video on beta oxidation, not on the release of fatty acids. So we're just going to be assuming we already have the fatty acids. But to really dumb down what beta oxidation is, once we've got our fatty acids, they will be transported into the mitochondria of a cell where beta oxidation will take place, where they will be converted to produce acetyl coenzyme A. Now, acetyl coenzyme A may sound familiar if you've ever done aerobic respiration, which is basically the use of glucose to produce energy. The way that energy is produced is by the use of NADH and FADH2 produced by the Krebs cycle, which will then donate protons and electrons into the membrane of the mitochondria, which will then leave to produce the energy to make the ATP. And if you would like to learn about it, then there is a video on it. Look for the ETC and oxidative phosphorylation of aerobic respiration. But getting back to this, these two are mainly produced by Krebs cycle. And Krebs cycle uses acetyl coenzyme A, so beta oxidation is the oxidation of a fatty acid to produce acetyl coenzyme A to produce proton carriers from the Krebs cycle. This essential reaction is not just one reaction, it actually takes place in 4 steps, the first of which being oxidation. Remember that oil rig. Oxidation is loss, reduction is gain. So oxidation is our first step, will be the loss of electrons. Our second step is hydration, and I will give 20 quid to anyone who can guess that. That's a stupid idea. Our third step is oxidation again, so getting a bit of a theme going on here. We've got oxidation, hydration, oxidation, and then our fourth and final step is thiolysis. The bit that matters in this is the same as what matters in most things with this word in it. It is lysis, being the splitting. So we're going to split something, and that's going to lead to the release of acetyl coenzyme A. The thiol means it's done by thiolase. It's a little bit irrelevant, but just remember those 4 steps and the essential components is the production of acetyl coenzyme A by oxidation, hydration, oxidation, thiolysis. To get into it though, we're going to act as if we've already got our fatty acid in the cytoplasm. Now remember that a fatty acid, for anyone who doesn't know what the skeletal formula is, each one of these points here represents a carbon, and you should be able to work out how many hydrogens are. If you are looking at beta oxidation, you should probably know this anyway. But a fatty acid is a hydrocarbon chain, meaning it's only hydrogen and carbon, ended with a carboxylic acid or carboxyl group. This is what makes it a fatty acid, because it has this hydroxyl group here, which can dissociate that proton. And an acid, the definition of an acid, is a proton donor. So that is why it's a fatty acid, a hydrocarbon chain attached with a carboxyl group. Problem is that can only get into the cytoplasm, not into the mitochondria. So if I just draw out quick mitochondrial membrane here, as you can see, it is incredibly accurate. I'm just going to signify that with cyto for cytoplasm and mito for mitochondria. So we have our fatty acid to begin with, shortened to Fa. That must first be activated. So it joins with coenzyme A, and that will produce acyl coenzyme A. If that name's confused you, it's actually very simple. So coenzyme A is literally just that sulfur CoA. That's how it's usually referred to. So we have our fatty acid here with our carbonyl and our hydroxyl group to make up our carboxylic acid. Acyl coenzyme A is simply the removal of that OH group to produce this molecule, which is acyl coenzyme A. All we've done is join coenzyme A onto the hydrocarbon bit to carry the hydrocarbon. There is still a problem here, however. Acyl coenzyme A can still not diffuse into the mitochondria, but it does allow a way in which the acyl group can get into the mitochondria. This acyl coenzyme A, which is essentially now an activated fatty acid, will react with a molecule called carnitine, which is just a carrier. That will then produce acyl carnitine. Of course, that will release our coenzyme A, and that will just be reused. So we have our acyl carnitine. This can now diffuse into the membrane and into the mitochondria. Once inside, the acyl carnitine will then react with another molecule of coenzyme A to reform acyl coenzyme A. It may seem a bit long-winded, but the whole point in this whole process is just finding a way to get this hydrocarbon chain inside the mitochondria as acyl coenzyme A. Of course, that will also release carnitine, which will just diffuse back through the membrane to be reused. So, now after all that, we have our acyl carnitine inside the mitochondria. We have our acyl coenzyme A inside the mitochondria. So, let's draw this out. We'll have our R to signify the rest of the molecule as a hydrocarbon. And then we have our hydrocarbon chain here. CH2, CH2, being CH2 because carbon makes 4 bonds. Then we have our carbonyl group left over from when it was a fatty acid. And then the coenzyme A group, which it is bound to. Now, as mentioned in the intro, our first step is oxidation. If you remember our oil rig, oxidation is loss of electrons. So the easiest way to lose electrons is in the form of hydrogen, because hydrogen has 1 electron. So at this point, we actually have a molecule of FAD coming in and FADH2 coming out, otherwise known as reduced FAD, because reduction is gain. That's gained those electrons from the hydrogens. This FADH2 can, of course, be used in oxidative phosphorylation. If you'd like to know how, watch that video. It's linked at the bottom. So, to be oxidized and to lose those 2 hydrogens, it must have lost those 2 hydrogens. So let's just quickly draw this out. We have our R group to signify the rest of the molecule. A little bit of a hydrocarbon there. Starting off basic, carbonyl group, and then our coenzyme A. So we've lost 2 hydrogens. We've lost 1 from here, and we've lost 1 from here. Carbon must make 4 bonds, so these 2 will make a bond with each other. So there's a double bond there. I'm going to draw that a little bit neater, actually. Oh god, this is not going well. There we go! So we've got a very neat drawing of a double bond across these 2 carbons, each of which with 1 hydrogen, each of which making 4 bonds. The name is actually very easy to work out from the structure. We started with an acyl coenzyme A. We've got a double bond between carbons 2 and 3, and they are transverse. So that is called trans delta 2 acyl coenzyme A. So trans delta 2. It's delta. Delta signifies a double bond within a molecule. The 2 above it signifies between which carbons that double bond exists. So it's not going to be any other number, because carbon 1 in any chain with just a carbonyl will be the carbon attached to the carbonyl, because that will have priority. There's no other carbons here, and they're all hydrocarbons. So that makes that carbon 2 and that carbon 3. It's trans because the hydrogen on each carbon are on opposite sides of the double bond. If they're on the same side, then it would be cis delta 2 acyl coenzyme A, because cis is short for cisamin, which is German for same. But you don't really need to regard that. Just remember that these hydrogens are on opposite sides, trans delta 2 acyl coenzyme A. Right, I'm going to stop rambling about that one and move on to the next one. Hopefully you remember that the next step is hydration. I was not being serious. I really don't want to give anyone 20 quid if they guess this, because it is so simple. So obviously it is hydration, so water must be going in, and of course water is H2O, which means two hydrogens and an oxygen are being bound onto this molecule. So starting with our hydrocarbon bit again, with our R and our little bit on the end to show what's going on. Draw out our very basic structure. Carbonyl group, coenzyme A. So for a hydrogen and an oxygen, we have one hydrogen being joined on here, making that H2 rather than a H1. We've gotten rid of our double bond because obviously they can only make 4 bonds. And we've actually put the OH onto this carbon here. We can now work out the name. So this molecule is called L3-hydroxyacyl coenzyme A, because we have a hydroxyl OH, hydroxy, on carbon 3 of an acyl group, an acyl molecule joined onto coenzyme A. The L bit just signifies the type of isomer that it is. If you've read the post on monosaccharide naming, we talk about D and L isomers. An L isomer signifies that the final OH, the OH on the final chiral carbon is to the left of the carbonyl group, whereas a D isomer, that OH on the final chiral carbon, is to the right of the carbonyl group. I'm not really going to get into that here because we're not going on about naming. Read the monosaccharide naming post if you'd like to understand that. But essentially, this is L3-hydroxyacyl coenzyme A. And this is really skipping. So, our third step is, of course, oxidation again. And our oil rig. Oxidation is loss. So we know that we have lost electrons, and how do we typically lose electrons? Exactly. So we have our NAD coming in, which will then leave as NADH, as well as one extra proton because it will probably dissociate its electron, signifying we have lost 2 hydrogens. So if we draw out our molecule again, here's our hydrocarbon bit. Draw it out simple. Carbonyl group, coenzyme A. So we have lost 2 hydrogens, neither of which are from this one. We keep our CH2 here. We actually lose 1 hydrogen from here and 1 hydrogen from here. And carbon must make 4 bonds, so it produces another carbonyl group there. We know that this is a ketone group because it's in the middle of the chain. An aldehyde's on the end and a ketone's in the middle. So we can work out the name again. This molecule is called 3-keto-acyl coenzyme A. There's a ketone group on carbon 3 of an acyl molecule which is bound to coenzyme A. This then brings in our final step, being thiolysis. Beta-oxidation is literally just the removal of 2 carbons in the form of acetyl coenzyme A from an acyl coenzyme A molecule. So all we're doing is splicing it there. And this is our lysis because it is thiolysis. So that then produces our acetyl coenzyme A. If you've never seen it before, this is an acetyl group. And that's a coenzyme A group. Quite easy to work the name out now. This is usually shortened to ACOA, or at least I shorten to it anyway. So if you see ACOA, that always means acetyl coenzyme A and not acyl. The acyl bit is actually over here, because this is still just a hydrocarbon chain bound onto our coenzyme A. The only difference is it's 2 carbons shorter. And that brings in our definition of beta-oxidation being the removal of 2 carbons in each cycle as acetyl coenzyme A. So this is, yes, indeed, acyl coenzyme A. It's just 2 shorter. This process will repeat. We'll have each of the 4 steps repeat over and over to this acyl coenzyme A down here, each time releasing an acetyl coenzyme A, until eventually we're left with an acyl coenzyme A that is only 2 carbons long, which means that it's not an acyl coenzyme A anymore, it is acetyl coenzyme A, which has 2 carbons. If you have an odd number chain, however, you will not be left with 2 because it's an odd number. You will be left with 3 carbons bound onto that coenzyme A. By the way, of course, you need to input coenzyme A here. I'll write that on. So you will be left with 3 carbons bound to that coenzyme A, meaning you're left with propanyl coenzyme A and acetyl coenzyme A. But that propanyl coenzyme A can be converted into acetyl coenzyme A later on in a different reaction.